As we just mentioned, atmosphere is the most important part of our confined space rescue. We need to know what's going on in the space before we can make our strategies and tactics and move forward. So with the atmosphere, we're going to ask 4 questions, and we're going to research those 4 questions in order to provide you with a better understanding of what you need to do before you send people into the hole. The first question we're going to look at is going to explore the relationship between dilution and air exchanges. So question number 1, what is one air exchange? Is it A, the volume of air equivalent to the volume of the space? Is it B, the complete replacement of air inside the space? Or is it C, the minimum air required to maintain a clean, respirable air in the breathing zone? Now, a couple of things so that we're all on the same page. Clean, respirable air. It's used in some regulations. What we're looking at with clean, respirable air is what we walk outside to any given day. We're going to look at 20.9% oxygen. We're going to look at no explosive or flammable vapors, and we're going to talk about less than 10% of the allowable limits of any concentration of another gas. So clean, respirable air. Whether we're in Vancouver, whether we're in Denver, we're getting the same thing there. The other thing we're going to need to understand is when we talk about ventilation, we are primarily talking about positive pressure mechanical ventilation. That's what we're going to discuss in this particular program for rescue. There's other types. We're not going to go down those wormholes right now. So, an air exchange is the volume of air equivalent to the volume of the space. However, it may require multiple air exchanges to completely replace the air in a space. What? Yeah, if you introduce a unit of air into a space, it does not remove an equal unit of contaminated air. It's not like we can just go in and just vent out the bad stuff. We're going to vent out good stuff as well. So we're actually diluting, not doing a 100% replacement. So there's a formula that we can use, and this is a theoretical formula. It works in a classroom. Once we get out in the field and we start taking things into account like stratification of gases, unequal mixing of these gases in a space, improper ventilation, we're not going to get this formula. But generally the formula looks like this. You take your desired amount of oxygen, in our case 20.9. You take the actual oxygen that's in your space. We're going to call it 10% for our example. And we divide it by 2. That's going to give you your new oxygen level. So 20.9, our 10% that's in the space, divide by 2. Our first air exchange puts us back up to 15.5% oxygen. We take our new number, our 15.5, we add that to our ideal, our 20.9, we divide by 2 again, we're up to 18.2% oxygen. As you can see, when there's more contaminants in the space, that first bit of ventilation works better because we're pushing more contaminants out. As the space gets cleaner, this gets tougher. Now we take our new number, our 18.2 on our third air exchange. We add it to our ideal, we divide by 2, we're up to 19.6% oxygen in the space. Our fourth air exchange, we take our 19.6 into our ideal, divide by 2, we're at 20.3. You can see our increments are starting to get smaller. The air is cleaner in the space. We are pushing out more clean air now than we're pushing out contaminated air. Our fifth air exchange, we're up to 20.6. Now in our theoretical 100% great world calculation here, our sixth air exchange gets us up to 20.8% oxygen. In reality, our gases aren't going to be mixed that clean in our space. Our ventilation isn't going to be that good, and we're probably going to be pushing 7 or 8 air exchanges in order to get this same effect. So let's take a visual look at this. Let's take a look at back to the basics with some Rescue Orange Kool-Aid. As you can tell, we've got our orange Kool-Aid sitting there. We've got a hose going into it, and we're going to push water in the bottom, much like our ventilation fan pushes in air into the bottom of our space. We're going to allow the water to come out the top, and flow over the sides, much like our air would. This is somewhat theoretical because our orange Kool-Aid is mixed pretty much evenly throughout our water. As you're going to see though, this becomes a bit of a science experiment because there are some variables that are more difficult to control. As we start adding units of water, initially, much like the formula, you can see large amounts of orange start to disappear. But there comes a point, all of a sudden, it starts getting harder and harder because we're diluting more and more to get the rest of that orange out. Now, in our demo turned science experiment, we did it over numerous times and had to come up with somewhere between 5.7 to 7.3 complete unit exchanges to remove all the orange Kool-Aid out of the water. So you can see from the theoretical that we just talked about, once we start putting into practical application, it changes. The takeaway from this, although an air exchange is equivalent to the volume of the space, you have to put multiple into them in order to ensure that you're putting your rescuer into clean, respirable air. It's good for them, it's good for your patient.